So, so this morning or this afternoon, we looked at, we proved theorems about the transform of the Heaviside step function. Thank you. About transforms of products of the Heaviside step function and other functions. We did the transform of the Dirac delta function as well. So at the bottom of page 55 then is this example which we just basically looked at the statement of at the end of the last lecture. So we'll have a go at solving this now. And then after it, I've got a past exam question as well that we could look at, which kind of features the Heavisides quite prominently. Okay. This is example 2.13, and we want to solve basically this differential equation. So the second derivative of y minus 4 times the first derivative is 3 times y is 6 times the Heaviside 2 minus 5. Okay, and this differential equation is subject to 2 initial conditions, to the 0 initial conditions. So both y and its first derivative are equal to 0 at time 0. Okay.
Not the second derivative.
I think I said it first by mistake, but the 2 initial conditions are just for y and its first derivative. It's the second derivative in the ODE, but the initial conditions. Okay. So as always, we're going through this 4-step process. First step is to transform the equation, then to bring in these initial values. Third step is to solve the transformed equation. And fourth step is to take the inverse transform. Although we've seen in the examples we've done, getting things ready to take the inverse transform can sometimes take some manipulation and preparation, sometimes requiring partial fractions, sometimes completing the square and the denominator polynomials and so on. Okay, so transforming the equation. And it's good to indicate what's going on. We're using the linearity and the transform of derivatives property. Transform of derivatives property or properties are summarized on the table of Laplace transforms. The linearity isn't mentioned on the table because it's so ubiquitous. Laplace transform is linear. It's built out of integration, which is a linear operation. Okay, so transforming, so the linearity means you're just going to transform each of these 3 terms separately and add their transforms together. Transform of the second derivative is s squared times y bar. Oh, and we'll just make a note. We're writing y bar for the Laplace transform of the function y. This is unknown to us. We can't do anything with that at the moment. So, but it features in the transform of the second derivative. And this is minus s times the initial value of y minus the initial value of the first derivative of y, s times that, and then minus the initial value of y. Then we got minus 4 times the transform of the first derivative, which is s y bar minus y of 0. 3y transforms to 3y bar. And the bit on the right side, we can make use of our table of Laplace transforms now because we proved it. But we just got 6 times the Heaviside. And the Heaviside transforms to e to the minus as over s, where a is the shift size there, which is 5. E to the minus 5s. Oh, God. I don't know what it is. Every time we meet s's, we tend to meet 5s right beside them. So it's e to the minus 5 times s, and this is all multiplied by 6 by linearity. So 5 is coming from the shift parameter here. These other new variables are s's. So you to distinguish your 5's and s's. Okay. This transformed equation can be simplified, okay, because it's got those initial values in, which helpfully in this example are zeros, the simplest kind of setup we can have. So really the left-hand side just amounts to the polynomial s squared minus 4s plus 3, all of it into y bar, and this is 6 e to the minus 5s over s. Okay. So that's bringing in the initial conditions, and now we're just one step away from solving it for y bar. We just have to divide both sides by that quadratic polynomial on the left. And at the same time, we'll factorize it. We'll notice that that is a nice factorization, s minus 3, s minus 1. So what we end up with is this rational function s times s minus 3 times s minus 1. And in the numerator, we have 6 times e to the minus 5s. Okay. So that's kind of like the end of step 3. In principle, we just have to take the inverse transform to recover our original solution. But now we notice we ought to pause and look at this thing and see how we're going to treat it, how we're going to take its inverse transform. It kind of looks like a rational function. It's like a quotient of polynomials. We've got this cubic polynomial in s on the bottom. But it's not quite a polynomial in s on the top. We've got this exponential factor. Okay. So that is going to cause the appearance of the Heaviside step function in our solution. What we're looking at there, what we're looking at here in y bar is really an instance of theorem, whatever it was, 2.5. Okay, that line that my pen is at now, what we're looking at in our expression y bar is some exponential. We have e to the minus 5s multiplied by an f bar, a transform of something. Okay, so the f bar in our problem here is our 6 over s times s minus 3 times s minus 1. So the inverse transform is going to look like this. It's going to feature the Heaviside h of t minus 5. That'll be fine. And it also features this function f evaluated at t minus 5 as well. Okay. So this is what the inverse transform is going to look like. So we need to identify what the function f is. Okay. What function f is having its transform f bar sitting there multiplying our exponential. That's what we have to arrange. So this is theorem 2.5, I believe it was, from this morning, or earlier this afternoon. Remember, that table is with you in the exams and that, so it's okay. So we'll just kind of indicate this now. So our function y of t is going to be the inverse transform of y bar. Well, let's bring out the 6 as well. So this is going to be 6 times the Heaviside h of t minus 5 times the function f evaluated at t minus 5. And what is this f? This function f is the inverse, where f of t is the inverse transform of the other bit, 1 over s times s minus 3 times s minus 1. Yeah? Agreed? So this is by theorem 2.5, using the result, which is listed on the table. So we've got our solution in principle, 6 times the Heaviside times this function f evaluated at t minus 5, but we don't quite know directly what the function f is yet. But it is the inverse transform of this one. Okay? But in order to take the inverse transform of this, of course, there ain't any functions exactly like that in the table quite yet, so we need a partial fraction expansion, okay? Because we can expand this into a sum of three rational functions, something over s minus 3, something over s minus 1, and then we can inverse transform each bit and add the results together to identify our function f, okay? So we need a partial fraction expansion. We need the PFE, partial fraction expansion of this quantity here, 1 over s minus 3, s minus 1. So this is going to be some a over s plus some b over s minus 3 plus some c over s minus 1. And yeah, I mean, I don't think I can do these 3 ones in my head. If it's a 2-1 like that, I can usually do it in my head, but these 3 ones, you know, there could be fractions involved in the a's, b's, and c's, so you might have a quick way of doing it, but I tend to just push it back together as a single rational function, keep track of what's happening to the a, b, and c. So a has to multiply, well, we know what it is, because it's a is multiplying s squared minus 4s plus 3, the product of these two. B is multiplying s squared minus 3s, product of, no, s squared minus s times s minus 1. And the c, that multiplies s squared minus 3s. So I'm multiplying as I go, but you know, each a, b, c is multiplied by the factors from the denominator that it doesn't have, that isn't over. So a is multiplied by those two, b is multiplied by first and third, c is multiplied by the first and second. And I multiplied them through as I went, so we can quickly pick out, comparing the two numerators. So what you see, these two fractions are the same, they got the same denominator, so they must have the same numerator. Different looking fractions can be equal, but if they've got the same denominator, they must have the same numerator if they're going to be equal. This is a polynomial in S. That's a rather simple polynomial in S. The only way they can be equal is if their corresponding coefficients are the same. Okay. So equating coefficients of s to the power n in the numerators, from the numerators, we should get a system of equations in a, b, and c, which hopefully the solution will fall out of if they're not too bad. So what have we got in s squared? Well, we got a plus b plus c in s squared, and there's no s squareds in the first numerator. What have we got in s's? We've got minus 4a plus b minus 3c in s's, and there's still no s's in the top. And what have we got in constants? Well, we just have 3 times a. There's no constant term in the other two. And there is a constant term in the first numerator, it's just a constant one. Okay. So, well, at least we can immediately read off some of that. So a must be a third. A is a third, then and then we get a third plus b plus c equals 0, and minus 4 thirds plus b minus 3c equals 0. So the easiest thing to do would be to subtract those. Subtract those, 1 third minus 4 thirds gives 5 thirds. B's cancel, and the c minus 3 gives 4c. So c is, am I right? Minus 5 over 12.
I got C as minus a half. I got C as minus a half. Yep.
So what did I do wrong? So A is a third, 1/3 minus 4/3, BB, C minus 3C. So this equation minus this one.
In the second equation, it should be minus B. It should be minus B.
Yes, indeed. Minus B. So let's say that's a minus B, so let's add them instead. Let's add the equations to cancel the B. So we've got minus 3/3, otherwise known as 1. B's cancel, and minus 2C equals 0. So that does imply that C is minus a half, yeah? So what you got? Minus half, yeah. C is minus a half, and then B should be just there. Waiting for us. So B, take it from the first one. B is minus A minus C, which is minus a third plus a half. Goes to something over 6. Minus 2 plus 3. 1. B's 1/6. So we've got our A, B, and C. So we've got our A, B, and C, so that means we have our partial fraction expansion. So this F bar S we've encountered is a third over S plus 1/6 over S minus 3 minus 1/2 over S minus 1. Okay, so that's good because these three functions are definitely on the table. So that implies that F of t is, well, that's just a third plus 1/6, and that's e to the 3t. And this is minus a half e to the t. So I'm reading those inverse transforms from the table of Laplace transforms.
Most of the time.
So what we want to finish with is presenting our solution to the original ODE. So we go back a few lines. So y of t now, what did we say it was? It was 6 times the Heaviside h of t minus 5 times this f, but not this f evaluated at t minus 5. That's important, okay? So evaluating that at t minus 5, well, a third is still a third, but this is now 1/6 of e to the 3t minus 15 and minus a half e to the t minus 5. Okay? Because remember, we declared earlier when we quoted theorem 2.5, when we quoted theorem 2.5 earlier, it was back at this line, we'd said the solution y of t was 6 times the Heaviside times f, but both the Heaviside and f were evaluated at this shifted translated argument t minus 5. So we identified our f of t, so we just, that final step was evaluating f of t at t minus 5 as well. So our solution y is 0 everywhere before t equals 5. From the point t equals 5, it then switches on all this other stuff. So it switches on this combination of constant and 2 exponentials scaled by 6. Okay. Is that okay? Any questions at all on the process? So we've seen that overall process a number of times. That's maybe the first time we saw it featuring the Heaviside step functions. So any queries or clarifications I could give on that? Sorry? You can go at any time. No? Anybody can go at any time. So well, the best thing is exercise. Physical and mental. So mental exercise is the best thing. So this is from the 2005 exam. This is question 4. This is one of the optional questions. 2015. Still don't believe we're in.
Yeah.
When I was a young kid, I used to buy comic books, which was said 2018. That was like unimaginably in the future, but I still can't believe 2018. So let's work away on this. If you got any questions or queries at all, please ask. Picture yourself in May.
Yes, I just remembered before.
Half an hour left on the clock. You've still got time for one question.
Oh, just get lost. It's okay, mine was 3. That's not No, I will.
Well, I mean,
I was born in 1995.
yeah.
I would have turned 9.
Yeah, so you were 9, so we were about.
Yeah,
but we were not before.
I'm just saying that I
We were talking about remembering before. Oh.
I remember the turn.
It's okay, my brother was born in 2009. I mean, my sister was born in 2006. That is good. I'm used to born in 2002. See, like, I don't mean this. I always think say that again.
I didn't think I was getting old, and then I met you and you more.
You're not old. I just happen that my oldest sister is the same age. It is funny that she's really like me. I mean, that happens to me. I happens to me frequently.
Not footsie, because she was stroking my ankle. I haven't even read the question. I can't read the question. I put my glasses on to try and read the question, which is far away.
I don't like it.
It's outside the interval. Yeah, but I don't
I mean, in general, a line right like high.
There's the air physics function which is 0 outside the interval.
Whether or not you're
But slope -1. Coefficient of t is the equation for the line is -1.
And the interface.
What is the point of it? Yeah. Yeah. Why did I get right? Oh my God. Outside of zero. Oh, right. I understood that. Thanks for that little explanation. Oh, yeah.
So maybe you got to part B, maybe you haven't, but to persuade you along, let's look at what the Laplace transform will be. So using that given expression for f in part A of the question, we'd simply read off the transform of each part, each of the three terms using the table. So t times h of t, well, the presence of h of t, remember, we only take these Laplace transforms with t beginning at 0 anyway. So the Laplace transform of t times h of t would simply be 1 over s squared. But you can apply the formula for something times Heaviside anyway, and you'll just end up with an exponential e to the minus 0s. Shift to 0 there. That's just going to be 1. Then you got minus 2 times t minus 2 h of 2, h of t minus 2. So that's e to the minus 2s over s squared. Because the function that's evaluated at t minus 2 is just, again, the identity function, y of t equals t. So it's, again, its transform, which is here, is the modified by the exponential. And then we have e to the minus 4s, again, over s squared. So that's our Laplace transform of f. So we could now launch into part C, solving the differential equation, featuring that f of t in the right-hand side. Yeah, so this bit generates the upward one. But it's only applies between 0 to 0 everywhere. Between 0 and 2 it generates t, so that generates the first result. The second one is turn on this function minus equals 4.
If you look back, have you written this what he's written down? So if you look here.
Using this general principle, this difference of heavy sides is switched on, one. Zero. Yeah. That's
Read the notes. I mean, I don't know, but I'm not sure it comes from how we define looking at it.
Yeah, so he's rearranged it. He's rearranged. So this has been rearranged from this. So this gives you, so it's like, yeah, so it's like he's looking at that.
Yeah.
I don't know.
The reason we repackage it like that is to prepare it for theorem 2.5. So every bit is, the bit multiplying the heavy side is expressed in terms of the same shifted argument. So it's parceled up ready for the application.
I think you get it. I think you're just telling yourself you don't get it.
What I cannot do is explain how
But I think that line that he's written does.
So this line, yeah, so what's going on here, yeah, so that's just the answer. But the explanation is here. So fundamentally, the function f is 2 bits, this bit and this bit, yeah? Remember the difference of heavy sides with A and B here, that difference of heavy sides is the function that's switched off everywhere, except it's switched on with a value 1 between A and B. So we use that as a fundamental device. So we switch on t between 0 and 2. So that generates this first segment. And this part will be 0 everywhere else, outside of 0, 2. Okay. But then we got to produce something for the second segment, so that switches on the second line between t equals 2 and 4. So it adds those values to the graph. And this bit is 0 everywhere else, so it won't interfere with what we've already generated here. And this bit doesn't interfere with this, because they apply in, they're non-zero in disjoint intervals.
Why people just why don't sometimes
because it's like fully understand what this means, fully understand what that means.
Generates these values.
Yeah, no, I feel like when you start trying to explain it, you just
she was like, I know, I get that. And I get that. I was like, don't you get it? What the fuck is your problem?
We don't want to reduce the value 1, we want to reduce multiply.
Well, what they do is say, like, solution B is not find what method about the solution is different.
So we just gave
Heavy side. Difference of heavy side.
no maybe. Then we just use that. Okay, so why double dot? So now you want
Why not? 27. I need my little charts. Oh my god.
Sorry.
I don't know.
this is a good one. What's the I'm just gonna copy you guys. What does one
Okay, transform the equation. That's the first step, transform the equation. Sorry? The ODE, the differential equation. Transform the whole equation using the transform derivative step. Just like we did in the last. Because the f is sitting on this side, so you're going to have to transform the f. So you've already got the transform of it from part B. So you transform both sides of the equation.
Well, I need to transfer one.
Well, on the left-hand side, transform 27F, right?
I'm trying not to. No, you're not. What? No, she probably is.
So let's look at how our equation would look when we begin to solve it. So we transform both sides, again using linearity in the transform of derivatives properties. So again, we'll write y bar for the transform of y. So what we'll have here is s squared y bar minus s, first derivative value, minus the value of y. That's a bit simpler now because we don't have a first derivative, so we just go straight to plus 9y. And that's going to be 27 times this expression here. Now we'll save ourselves a little bother. Let's call that expression capital F of S. There's no need to keep reproducing it all the time. Next, we'd introduce our given initial conditions, which simplify it again a bit. So we go to s squared plus 9 now, times y bar equals 27 f of s. Well, it's got s squared y bar and 9y bar. And these two are going to disappear because they're both 0. Yeah. So our function y bar, now I'll bring back in, I'll split f apart here. Remember in f, the terms in f all have the denominator s squared. So I'm looking at 27 over s squared times s squared plus 9. And that's multiplied by these exponential bits, which is 1 minus 2e to the minus 2s plus e to the minus 4s. Now it makes sense to leave those packaged together. Yeah, because like in principle, that's the end of step 3. We've solved the transformed equation. Got it here, and now as our solution for y bar as a function of s, we just have to take the inverse transform. Now we could use linearity. If when you multiply that bracket out, you've really got 3 terms. This fraction minus 2 times the exponential, this fraction, plus the exponential minus 4s, this fraction. So we could use linearity to take the inverse transform of each part. But each part is this function of s, either just on its own or multiplied by an exponential. So they're all going to require that property about transforms of the Heaviside step function. So taking in first transforms here, this will require the use of theorem 2.5 So we need to identify g of t, which is the inverse transform of this function, 27 over s squared plus 9. Okay? Because applying theorem 2.5 will require us to evaluate this function g of t, the inverse transform of this part, at various shifted arguments, t minus 2 and t minus 4. Now this denominator is a little bit complicated. So we got an irreducible quadratic and a power 2 of s. And it would be potentially the partial fraction expansion would potentially be quite complicated if the numerator were at all complicated. If it had any s's or s squareds in it, things might get quite hairy, and you might have 1, 2, 3, might be 4 parameters to determine here. But because it's just the simple constant 27, we can shortcut things. So notice how the PFE falls out, let's say. Or, you know what I mean, falls into our lap as, what's the partial fraction expansion of this going to look like? Well, it's just a constant. So I'll be able to generate it like this. How do I generate 27? Well, if I stick a 3 up here, when I collapse the two together, that 3 will multiply s squared plus 9. The 3 times 9 gives me 27. The 3 times s squared will give me 3s squared, which you can't see here. So I can cancel that away by putting a minus 3 here. So that's the partial fraction expansion of those two. These two functions we do find on the table. So if we'd had a more awkward numerator there, we'd have to go through the full process of finding a partial fraction expansion. But it was set up nicely for us. So our function g of t is 3t minus 3 times the inverse transform of 1 over s squared plus 9. Oh, no, in fact, not minus 3. That's just minus the sine of 3t. If you look in the table of Laplace transforms, there'll be an entry which is omega over s squared plus omega squared. That's the transform of the sine function, sine of omega t. So that's our function g of t. So now we can take inverse transform of y bar using theorem 2.5 to get y of t, our solution that we need. Well, the first bit of it is just this g of t. The next bit is minus 2 times the Heaviside step function h of t minus 2 times g evaluated at t minus 2. And then the final part comes from this exponential e to the minus 4s multiplied by our 27 over stuff, which gives Heaviside h of t minus 4 multiplied by g of t minus 4. So this is our solution to the ODE. Three terms featuring this function g multiplied by various Heavisides. Okay, so I was a bit cursory there. If that was an exam situation, remember you would have had at least half an hour for that full question. So you would want to make additions there, sufficient additions to demonstrate your understanding and justify and explain some of those key steps, okay? I was a bit speedy there.